Is this? Okay. I feel like it still stays on. So turn my. Let's do it. Hello? It's not that bad. Hello? Do you know how to get back there? Still does that. Hello? Hello? Oh, cool. Okay. Okay, so let's get it. Um, these are the main topics for y'all's exam 3. Let's start with MIPS. So, get my notes. So this part is what is y'all are gonna get on the exam with you guys, okay? And this side is just we're giving you how each of the lines of code would look like. So that's the load. This is store work, add immediate, add, subtract. I don't think y'all need all of these for the exam. Just this side, and then these two, I believe. So yeah, y'all don't have to memorize the chart. You will be given this, but do remember how the lines of code are. So for the load word, which side is what? And for addition, we're gonna have 3, but for the load and the store, we're just gonna have 2 of the register files, and then this is just the number.
So you're saying they're not gonna give us that on the right side?
No, the exam is just gonna have this side. This is what you're given, but you'll have to memorize all of these. Yeah. Um. So yeah. So in total, we have 3 different types for machine code. This is also given in the exam, but I'm just gonna go over it. So the R type, this is the add, subtract, multiply. There's another one, but y'all only need to know the 3. So we have the 6-bit opcode, and then this is the RS, RT, and RD. So the RD is where you store it, your data in. RS is like the first number that you access, or the first register file that you access, and this is the second one. And then this is just the 6-bit code. There's the I type. These are the ADDIE, the load, and the store work, and also the BNE and the equal to. This is just the is it equal to or DNE? What was that?
BQ.
That's equal to, and NE is not equal. Yeah. We'll go over it later, but essentially this one we only have two of it. We don't. So the load work and the store work is where we take data either from the data memory or the register file, and then we read it from one of them and you write on the other side. So that's why we only have the RS and RT. We don't have a RD. Does that make sense?
Sorry, which one's the destination? I guess the because it's like
So
the destination is.
well, it depends if it's a load or the store work. We'll go over it later, but essentially, either the S is the where it goes in, or the T is where it goes in.
Okay. Yeah.
Yeah, we'll go over it after this. I'll go over it, and then this is just the immediate number. And JTAP is just when we jump. So we have the opcode for the J, and then a pseudocode, which is the label, and we'll go over that as well. So this is one of the questions that y'all are going to be asked in the exam. So this is the load work, right? So before we go into the question, we should understand what the line of code is, right? So this is the load work, right? And what does the load work do? It takes data from the data memory. So this is the data memory. This is what gives from the data memory, and this is where it stores it into the register file. And this is also the register file. So to find the data memory, it's basically we take whatever content is in this register file, so at T6, and then we add 8 to it. Does that make sense? So the formula is whatever this is, whatever data is in T6, we add that with whatever number we have right here, which is 8.
14?
Sorry?
Is you saying that'd be 14?
No, whatever data is in 6. So T6 is this number.
Okay.
Yeah.
So 288 is
Yes. Yes. So our data memory is 288. And whatever, and we're going to store two. Actually, I don't think I wrote what's in the data memory. So, for example, in 288, we can put, you'll be given this. This is, I just forgot to write it on the slides, but you'll be given whatever is in the register file and then another box that says like different data memories and what's stored in the data memory. And this is just an example that I put in. So you'll be given the data memory as well. So, so here we found that 288 is our data memory, right? And then we look at what is in the data memory, which is 243. So we would add the 240, we would write the 243 into the T4 register file.
Where did you get the 243?
This
Oh,
is
you said
given.
this was given.
Yeah, this is the given number, but I just didn't write it on here, so. Yeah, does that make sense? Right, so on the actual design, we only have 2 register files, right? So we don't even need or we're only reading this one, or sorry, my bad. We're reading this one, and we're writing into the T4. So we don't need the other write at all, the decoder. So what you can do if you're given, you just write the enable is 0, and all of this, you can just cross it out. Does that make sense? So.
Guys, maybe use a darker color.
Oh, my bad. Div red. Yeah. Okay. So this is just, you don't need it because we're only reading from one of them. So all of this would just be X. Yeah. So, you can start either way, but let's start with the read. So, so we have the read as enable. So this would be 1, and we're also writing it. So the enable is 1 for both of them. And when we're reading T6, right? So in the adder, we write the 6 in binary. So the binary for 6 is 110. And so we're accessing D6, so you just put 1 here, and then the rest of them are just 0.
How do you know you was reading from the D6?
Because it's given T6 right here.
Oh, Jesus. Okay.
Yeah. So the data number we got from there is 280. We don't write 288 because in T6 it's actually 280. And then we do the math, which is 288. Yeah.
So like, so that's in that's in decimal, the data.
Yes. Yeah. The data is in decimal because.
So we do, okay, because I just remember like, so it's not in hex. Okay, never mind. Okay,
No.
so it's in decimal. Okay.
Yeah. Yeah, so we did the read. Now we have to write it in T4, right? So you have to enable the write, and the adder, this should be 1100 because it's 4. And you write 1 next to T4 and then 0 for the rest of them. And the data we're writing is 243. So we write 243. Does that make sense? So
So we start right to left, or is that, or can you start?
You can write it either way, but the way it works is you first go find you read the data, and then you add 8 to it, and then you write it.
Oh,
So technically, if you're doing this as a question, you could do it, but like to like understand it better, just do it how load work works. So it first reads it, and then it does the 8, and then you write it. So yeah.
and we did one more question for the first one. We enabled. I mean, that was a 0 for because we didn't need it. You said.
Yeah, because here in the question, this one, we're only reading it from one of the register files, and we're writing to one register file. So we're not reading twice. We're just reading it once. So we only need one decoder for read. We don't need the other one. So you just put a 0 and then, yeah. So moving forward to the store word is basically opposite. So you take data from, so here, so this is the data memory again. Sorry. My bad. Data memory. And so we basically read it from the register file, and then we do the math. So whatever the number is here, 640 minus 12, it's plus negative 12, so just minus, which is 623. And this is where okay, let me get this straight. So we're reading it from this, so we're storing it, right? So we read it from this register file, and we write it to the data memory. So in the load word, we did the opposite, right? We took the data, whatever is in the data memory, at 288 data memory, and then we wrote it to our T4. But the store word, it's opposite. So you read it from here, and you write it at the data memory. But in this one, we don't actually write it because this is the register, right? So we're writing it, store width is writing it to the data memory. So when it's this question, you don't write it anywhere. So there's actually 2 reads. You're reading 2 register files, so you don't have a write enable. That's 0. Because we're writing it to the data memory, not the register files. And this is for register. Does that make sense? Okay. So, and for this one, to know which of the 2 read files, which one should go where. So if you look at the first question, right, in the data memory read, we put the 6 in the furthest away column, right? So same thing, just follow that. Yeah. sorry, give me 1 second. No, I said it wrong. The 6 is here, not on the furthest away. It's right here, right? Which is the read. So same thing. The register file from in the data memory equation, that one would go here. So T7 would go here. So from that, we only have one read left, right? So the T5 goes here. And it's the same thing. We do enable 1. There's no write, so all of this is just X'd out. And 7 is 1, 1, 1. And this is 1, 0, 1. The data at T5 is this. It's just 894 at T7 is 640. Yeah, and then you just, or 1 here and 1 here, and then the rest of them are 0. And the same thing on here. Any questions? Okay. Yeah, so this is for the B and E and BEQ.
Sorry, can you scroll back up to so we got the value from D7.
Yes. 6. Oh, I switched it. My bad.
Yeah.
Should be the other way.
Okay. Yeah. Okay. Yeah. So when we apply the negative, we don't put the -12 there. We just take the straight value.
Yes.
Okay.
Because when we do the negative, it's in the data memory, right? And in this question, it's just about the register files.
Okay.
So we're just reading it from the register file. We're not doing any math
Got it.
in this part for now.
Okay.
Yeah.
Got it. Okay, I understand that.
Yeah. So this is 640 and 894. So if we go back here, right, for the B and E and BEQ, we have a immediate number. So you have to memorize this one. This is just the address of the label minus the address of the branch plus 4. You have to memorize this. And then when you do the IMM, right, so you're going to get a binary number, right? And it would always end with the 0, 0. Because it would be a multiple of 4. Does that make sense? So you would just remove these last 2 bits. It would usually be 1, 1, or whatever the numbers are here, right? I'm talking about the 16-bit code from this one, this part.
I thought we did that for jump. Like, I'm confused. I thought we didn't do that for the B equals. I guess I might be wrong. Like, I talked to my professor once, and I thought we didn't do it. I might be wrong, but I thought you didn't do the takeaway the last 2 bits for the B equals. I thought we just did step 1. But like I don't know. Like I might be wrong. Like maybe I misunderstood my professor. So I remember because I remember playing for jump commands. I do recall the whole take the last 2 bits off.
No, you do for the I-type, yeah.
So, okay, I guess I'm home.
Yeah.
Have that homework on.
Yeah.
Okay. Make sure to remember that for this exam.
Yeah. So the IMM is just the label address minus the branch plus 4. And this, you have to do it you just have to memorize it. You won't be given the question, and then, again, you have to take the last 2 bits. So it would always be 0, 0. So that's like a way you can check your answer as well. Like if it's not, maybe something went wrong. And yeah, so for this one, wait, let me pull up mine. Okay, so This one, if you remember, the add is a R type. Here, this one. So we're gonna have a 6-bit opcode, RS, RT, RD, a shift, and then the 6-bit code. So the opcode for add is
Would it be an addy command?
addy is add immediate.
Well, that it says 25. Isn't this that's an immediate?
This is add.
Okay.
Yeah. No, actually, yeah, you're right. It should be add immediate. Add immediate because we have a number. So this basically add immediate is where we
So if you have a number in there, that's an addy.
yes. Yep. Sorry, give me 1 second. Question actually. I lost my. I'll come back to the question again, okay? So this is where actually, do you mind going over your stuff? I'll come back. I'll come back to these questions.
So we're gonna go over information as now. This is stuff that you guys, I think, had on exam 1, so I'm not gonna spend too much time on this stuff, but just ask questions if you have any. So in this class we learn about 4 different kinds of like bit types. So we have decimal, which is base 10. We have binary, which is base 2. We have octal, which is base 8, and we have hexadecimal, which is base 16. You guys really need to focus on binary, decimal, and hexadecimal. And make sure you remember the bases because it's kind of easy to get confused with those 3.
And we'll post the slides on Discord so you.
And a recording on YouTube
Yeah.
as well.
Oh, it's on YouTube.
Yeah, we're recording and then we'll post it on YouTube. Okay. Number system representation. So this is when you're converting from binary to decimal. You use since it's base 2, you just do 2 to the power of 3 to the 2 to the power of 2, 2 to the power of 1, 2 to the power of 0 to get the value. One thing to remember is that it starts at 0 and it goes this way. I always got confused, like, because I would always start at 2 to the power of 1 instead of 2 to the power of 0, but you always have to start at 2 to the power of 0 and then you go that way. Okay. This is just a summary of how to convert each one. Okay. Do you guys have any questions about that, or it's pretty straightforward? Okay. Two's complement? Yeah. Okay, so we're gonna go over two's complement. This is basically a way that we represent negative numbers, okay? So, so positive integers are represented as is. Negative integers are formed by inverting all the bits and adding 1. So that's the reason why it's called two's complement. First, we invert all the numbers, which is the ones complement, and then we add 1, which makes it two's complement. Okay, so there's something called an MSB, which is called the most signed bit. So it's the number that's on the very left side of a binary code, right? So if it's a positive number, the MSB will be 0. If it's negative, the MSB will be 1. Okay, convert the following signed numbers to an 8-bit representation. So we have 11. 11 in binary is 0, 1, 0, 1, 1. Since it's a positive number, the MSB is 0, right? If we're going to convert this into an 8-bit representation, we're just going to add enough padding of zeros to make it an 8-bit. Same with -9. The MSB is 1 because it's negative. If we're making it into 8-bit, we'll just add enough padding so that it's an 8-bit representation.
Can I ask you a quick question?
Yeah.
Say it's like 4-bit, that's gonna equal an 8-bit, right?
Mm-hmm.
Like a 4, so if it's like 6 and 6, that'd be 12.
Yeah.
So you're adding enough zeros to cover the 12, like you add
So
6 zeros.
yeah, so that's like in this question it specifically asked for 8-bit.
Yeah,
right?
I mean, I understand that.
So-
but I mean, if they don't ask
Y-
the question, I mean,
It's usually 8-bit.
it's usually gonna be.
It's usually gonna be 8-bit. I haven't really seen like they ask like 12-bit.
I mean, I know she always multiplies like 6 on 6, like 6
Really?
times 6. Yeah, so I never knew how many you were supposed to add.
Yeah, but yeah, even if it asks for 12, you just add padding to make it
Okay, make it-
based on the MSB. Yeah. Okay, so we're gonna do a quick problem. So what is the 8-bit 2's complement representation of -7? And then the hint, first convert to 8-bit and then apply 2's complement conversion. Okay. So we're gonna what's the first step?
Do the 7.
Yeah, so we can,
I mean,
so we'll convert it to binary first, right? So what's 7 in binary?
1, 1,
0, 1, 1, 1. Yeah. So that's our 4-bit, but we want it to be 8-bit. So what padding would I add? Would it be 0 or 1? Yeah, we're gonna add 0. So we're gonna forget about the negative right now, okay? Only take the negative at the end. So we're gonna add 4 zeros to make it an 8-bit. And then, so that's our first step. We're gonna do 7 in binary. Second step is we invert all of the bits, right? So inverted, the zeros would turn into ones, the ones would turn into zeros. So 1, 2, 3, 4, like that, okay? So this is our 1's complement. Then to do our 2's complement, we'll add a 1 to this number, so +1. 0 plus 1 is 1, and then all the other numbers stay the same. And that's your final answer. So that would be -7, okay? Okay, so binary machine code, Cash went over this. Are you gonna go over this again? Do you want me to go over it again? Or
You can go over it quickly because I have to do
Okay.
this one, right? Yeah.
so do you guys just want to do a practice on it, or do you guys want me to go over it again?
what is this?
This is the binary machine code, kind of like this stuff. The stuff we did here.
I
It's
haven't gone over there.
Oh, you haven't?
Yeah.
Okay.
Just-
So then how about let's just do it at the end?
Yeah.
Okay. We'll come back to that. Do you want to do registers now?
For the 2's complement, or y'all gonna do a multiplication on those?
No. So, okay, so if a question like gives you 5 times -7, you have to convert -7 to 2's complement, and then you would do multiplication. But this question just asks you just to convert it, so you don't have to.
Okay.
But if it was a multiplication problem, you would have to.
For the 2's complement, say if I had 5 ones I was trying to add, what does that equal up to?
5 ones.
Some-
Oh, like if I had 5?
Yeah, like 5 in a row. I know 4 gives you a 0, and then you add over the 1 and the 0.
0, yeah. Have you seen it with 5?
If y'all was gonna do a 2's complement question.
I haven't seen it with 5.
Yeah.
Now, every problem she's ever gave us, I mean, there's always been.
Really? With 5? I can look into that. I don't know. I haven't seen it with 5 yet. Okay. Oh, okay. So we're gonna go over register.
I think y'all went over this, but I'll go over it quickly too. So basically, in the register file, you have the read and the write. And whenever you do these questions, always in the clock, you always do the cycles. And the cycles always start when the line goes up. So whenever the clock goes to 1, because this is 0, 1, the new clock, so the new cycle starts whenever it goes up. So you see, this just goes down, and you just look at whatever number or whatever box it's intersecting with, and that's our number. Okay, that's how we do any of these questions. So for this question, we have a for register file with the read and a write. We have to find the R data. So we're trying to find the read data. So right now here, if you go through cycle 1, our enable is 0. So we don't read anything. And since we don't have any of the numbers before, usually you don't write 0 because you don't know what it is, right? So usually you just, if you're like doing it hand drawing, you just do it in the middle, just saying undefined. And usually in the exam, they won't ask you this. They would just tell you to start from A, like in this question, right? So let's go to cycle 2. If you just go down this line, the enable is turned on, right? So we do read whatever the number is. So this is 1. We'll go to cycle 3. Go down. The enable is still on, so we read the number 2. Cycle 4. Let's go down. It's turned off. That means we don't read new data. We just copy over whatever our old data is. So it's still 2. Cycle 5. This one, I know it's like right at the intersection. Let's just assume that it's on. Actually, I don't know. Let's just assume it's E, right? Because it's like right at the inter. Okay, wait. Yeah.
I have a question. So
Uh-huh.
the read enable is off, but the write enable is on. So the value of 900 is the value. Hold on, because like you're just writing down like what the address. That you're okay. So it's like you're writing down the address, but the W data is the value in that address, right?
Yeah.
And so like because like the write enable is on. So let's say that the rising clock.
Mhm.
There's the one when the read on C, the read enable is off, but the clock went to 3. So it would, even if the read enable is off, if we turned it back on, it would still have the value from 3 in it, right? Like, hold on, let me explain myself. Because like the read enable is off, so we're still just reading the previous value, right?
Mhm.
But the write enable is on, so we're still writing new values, right? So at that rising clock there with the 3, we would still be writing the value
This one?
in 3 addresses.
Are we talking about this one or this one?
I
Yeah,
think you have to go with the question though, too, to just determine the order that.
yeah, I guess it doesn't matter. Never mind, it doesn't matter. And like, we'll write Z for the first art elements. It doesn't matter.
I don't think we can. Can we can't use these, right? Yeah.
Really close.
It doesn't matter.
Does matter. We gotta pass this test. So why does if the read enable is high for D, why is it not 2 then still?
Okay, here, let me. If you see the cycle, it's. Okay, this question is weird. It's like right on the line.
Because nothing changes till it hits that line, right?
Yeah.
Because this is really weird. It's like it's oriented. It's like arranged differently in the problems I've seen before.
Look, usually it's like A through Z or A through H or I.
Yeah, it's like I don't know. This one's confusing me because I've seen before.
To be honest, I think I was gonna do this side.
See, it seems to me because it's like the clock rises in like the middle of like the B or whatever. Like that means that in this B period, it's going to have 2 values on it, right? In the same, like I don't know, it's confusing because like the clock rises in the middle of the A,
Right.
so it's going to have the value.
You know, I do see my teacher. Sometimes she'll split that box and then she'll have a number in that box, so the
Yeah.
previous number in there. And then once it hits the clock, she'll have the next number. And
Yeah.
in there she'll have that number in there.
Like before, because for an A, like before, because the clock rises during A, and before it's the value from 1.
Right.
But the clock rises again during the A period, and then it would be the value from 2, right? I mean, I think it's a very confusing question. I don't know, because like I don't know. 'Cause,
I understand exactly what you're saying.
yeah, but
right.
the thing is like the clock's rising in the middle of the period. I don't know. I find that confusing.
Do you prefer this one? Wait, what are the ones that you guys usually see?
Because I guess
It's usually from.
Do you guys have your Zybox by any
it's
chance?
like the clock usually rises at like the begin. Like honestly, the clock rises like the I find the E one less confusing. Like I find it less confusing.
These questions are like from when we took this class.
Yeah.
And we had
Yeah,
different
they're-
teachers too.
Because they what?
Teacher, I get it. That's why I was gonna ask y'all on hers. She'll have it from A to like J or whatever. And I was gonna ask you because I know you're supposed to do the rising clock, but the what's the other when it goes down? What's that one called? There's rising and lowering, not lowering clock. But like the clock when it goes down, when it goes from 1 to 0.
Yeah.
she wants a value for that too. So
Really?
I don't know if you're supposed to keep the same value or if it's supposed to be a new value or what.
I don't remember because for us it was just like just read it whenever it goes up.
Omnet and Core.
Yeah, he'll take. Yeah, that's why he's confused because our questions are totally different. Than
Yeah.
Like this right here, easily.
Yeah, this is. I guess like this is what the Zybooks
that's
looks
this
like. This is like what our Zybooks look like, I suppose. So I guess.
Let me pull up the.
This is what yours look like. Okay, so the clock it's right here.
She makes her questions very difficult.
Like, it doesn't. Cause I know some problems we have. They
Mhm.
don't talk about like the read and the write. These simplify. Just think, what is the value on the register? Like they don't complicate it.
Oh.
The write, asking, okay, what's like the write value? What's the read value?
Yeah, we never had one like this.
Yeah.
It's usually low and.
Right. Yeah. Like usually it's just like what's the value in the register? That's what we ask.
Dang, okay. Sorry guys, I don't know.
Yeah, I get that because like it's like different.
Yeah.
Like I get it. Let's
Which one is it?
I think pulled it 5.
Yeah, see, that's how hard. You're right.
Because like the AVAs are like because they
Mhm.
chopped up so each section started when a clock rose. So there was no like clock rising in the middle. Exactly like that. It looked exactly like the
This
below
one.
that.
Okay.
Like, that's exactly like what I was just looking at. Actually, that's like the exact. That's like literally the exact problem I was just looking at. Yeah, that's exactly the thing. Okay. So this one, this one, the kind of stuff. Right, because the clock rises at the
Mhm.
beginning of each period. So
Yeah.
there's like no clock rising middle.
Here. This one would be undefined. And here it's open, right? So this would be 7 because the clock rose here, and we have the data as 7 here. Again, it's still 1, so we take the data. It's 4. It's 0, so we don't read it. It's 2. Again, it's 1, so we do read it, which is 5. And so again, you read it, so it's, well, you don't need it, but it should be 4. And we skip 7 because just the way the clock works.
Yeah.
Yeah. Okay. But
I remember.
do you guys need to know this? I don't.
Yeah, I don't remember.
Yeah, we can go over that.
Okay. Yeah. So, did you have this?
Yes.
Okay. So memory, there's 2 big topics, right? So it's volatile and non-volatile. And volatile has 2, the RAM and the RF. Yeah. And then the non-volatile it has the programmable and non-programmable. And there's 2 types of RAM. So SRAM, DRAM. The RF is just 1. The non-programmable has, again, 2 mask, and then OT. Programmable and programmable, it has flash, EPROM, and EEROM. This one, to be honest, if you just read over the memory, you just have to kind of memorize it, how the questions ask, and you just have like.
It's like we're gonna get a problem. It's gonna be like, okay, this is
Like this.
We're gonna get a problem like this.
Yeah.
Damn, I hated that in the homework. That sucks.
It'll
Yeah.
give you like a scenario and you have to
Right.
choose.
Yeah.
Okay. Yeah. Well.
Yes.
But I remember for me it was extra credit.
Really.
Yeah.
That's good to know.
But I don't know if it'll be the same.
Who y'all teach?
It was an actual question.
For us?
Yeah, for finding.
For
This exam too, this was the extra credit.
Oh, for exam 2.
Who
Okay.
y'all teach?
Should be
Yeah.
Y'all didn't have our teacher.
Wait, who's your teacher?
Core.
Yeah, I'm net 4.
She switches up all her questions. This is like straight.
Yeah.
Yeah, she's.
Oh, she's the new one.
Yeah.
Okay.
This semester.
I feel like that's why we were having a lot of problems with exam 2 too, because we're
It's
one
all
of the
different.
exams a little different.
Really?
Yeah.
Not like just came out to the board.
Think I don't know if it was exam 2, but like during one of my tutoring sessions, someone came up to like and asked me a question that I had no idea, and I was like, I think it was like architecture question. I was like, I don't know.
We never
I
learned
don't know.
it.
But yeah, anyways, for these questions, you just have to memorize how these works, right? So I think I have answers on mine. So SRAMs are usually they're static, but they're fast to fetch data. So if you read the question and it sounds like you need to fetch data quickly, it's probably SRAM. So this is fast data fetch. DRAM, it's slow, but it stores a lot of things. When you read the question, if it sounds like the question you have a lot of data and you have to store it, it's DRAM. Mass, this one is just usually car keys. If it's anything about car keys, it's that one. And then it's OTP, right? Y'all know what OTP is, like one time. So this is usually if it's like a RF card or an ID card, is the OTP. And then EP1, I think this one is it's this one. So whatever it's like 1980s, it's EP ROM. And then here, 1980s, EEROM, EEPROM, that one. So anything that's like related to calibration. It's like a flash rush. So whatever, if you need to store any data, like that one. Yeah. So again, just go.
Store any data.
Yeah.
What's the difference between that and the DRAM?
DRAM is slow, and flash is like portable. You can take it anywhere.
So DRAM is volatile,
Yes.
and flash is non-volatile.
Yes.
Yes.
Yeah. And again, if this should be on y'all's exam too, so if you just before the exam, just look over this, whatever the questions are, and whichever associates with what. And
Are you going back to the? I'll go back. Okay. Okay. Again, I'm not gonna spend too much time on these. You guys pretty much know this, right? Okay. I'll review it again. Yeah, I'll go over that. Okay. So first gate we have is our AND gate. AND gate outputs 1 only if all the inputs are 1. And when you have an equation, it's denoted by multiplication. Okay, so these inputs are 0, so the output would be 0. But these inputs, they're both 1, so this would be 1. Okay, and it has a flat line like that. Okay. This is the OR gate. It's denoted by addition, and OR gate outputs 1 if at least one input is 1. So on these two, since at least one input is 1, the output will also be 1. And it has a curved line right here. Okay, last one is your NOT gate. This one, it's kind of like an opposite gate. So whatever the input is, it'll make it the opposite for the output. And it looks like this. It has like an inversion bubble and then the triangle. Okay. So next we have NAND. A NAND gate only, it kind of, think of NAND as the opposite of what AND is. So AND gives you a 1 if both inputs are 1, right? But on this one, if at least one input is 1, it will give you one of these ones. Same with these ones. If both inputs are 1, it'll give you a 0. It's kind of like the opposite. Then you have your NOR. So on your NOR gate, it's the opposite. So since at least, so on an OR gate, if one input is 1, the output will be 1. But it's the opposite. So if at least one input is 1, then the output will be 0. Okay? And then we have
I think
XOR.
NOR is kind of like extreme cases a little bit. Actually, wait, that's XNOR. So this one is like extreme. It's either both of them have to be 0, then it's 1, or both of them have to be 1. If it's any of the combination, it's 0. That's XNOR. Does that make sense?
This
Yeah.
one. Yeah, so there's odd parity and even parity. That's a good way to memorize it too. Odd parity, odd number of, what does it say? Input?
Of ones.
Of ones, the output is 1. Okay, and then XNOR even parity, if the even number of ones, the output is 1. Okay. Okay, so this is, yes.
Do you know like XOR looks like for like 3 inputs? Because like that messes me up. And do you just have like I can do that research on my own? Like, do you just remember off the top of your head?
Like what it looks like?
Yeah.
It would just look like that. You just add another line.
For 3.
Yeah.
Well, I guess like, I mean like in the equation. Never mind. I'll figure this out on my own.
Yeah.
Like that messes me up. Like,
Okay.
3 input XOR. Because it's like, cause I think so. Or I remember it's like in a K map.
Yeah.
XOR is like it's like a checkerboard pattern, if I recall correctly. But I think it's like, because I remember my teacher said if you use XOR, you'll get like extra credit on the exam.
Uh-huh.
So like I
mean,
make sure I get XORs right.
The way you draw it is just an extra line. As for the equation, it would just be like A, B, and then C, like that.
Okay.
That's the checkerboard symbol you're talking about, right? This
I
symbol?
remember it was like on a yeah. No, 'cause I remember like on a K map, you know how it's like you have the zeros and the ones.
Yeah.
So I think I recall it's like with an XOR, there's like a checkerboard pattern on the K map. That might be wrong because I've never. Like,
Okay.
I think I recall hearing that once. And it's like my teacher said if you use XOR in your logic gates, you'll get extra credit. So like, I want to make sure I know like XORs correctly.
Okay, I'm about to go over like a way to draw it. So maybe that'll help clear it out a little, okay? So this really important. Like if my biggest tip to you guys, memorize this. That's how I got that question right on the exam. I just memorized the way it looks like. So if your so this is for NAND, right? So if your inverter, if they give you an inverter, the NAND inverter looks like this, okay? Same with AND, the NAND inverter looks like this, or the NAND inverter looks like this, okay?
For the inverter, this basically means you're putting the same input twice. Does that make sense?
Yeah, that's why you.
Yeah.
Okay, and then NOR, basically the same concept, kind of switched. Inverter, looks like that. And the NOR version of AND is like 3 of the gates, and then OR, like that. Okay, so I'm not gonna do the example because it takes a while, but I'm gonna show you guys one of the examples I did last semester. So this was the problem they gave me. So this is what you guys will see on the exam, right? So you'll get an equation, and then you have to draw it as a normal circuit, convert it to NOR, and then convert it to NAND, okay? And then simplify. So this is just the normal way the circuit looks like. You guys know how to do this, pretty easy. This is how I converted it to a NOR, right? So here I have one inverter, so I converted it to the inverter of a NOR. Same with my OR gates and my AND gates, I just converted it to that shape. And then the way you simplify it, so do you guys see how there's 2 of these gates right here? They kind of cancel out basically, so you don't have it anymore for the simplified version, right? Yeah, right. And then same concept with NAND as well. If you have 2 of them like this, they cancel out, so you don't have it anymore. Okay. Just show you guys that. Yeah. Okay, so binary arithmetic. So this is where you do all that multiplication, twos, complement stuff. So we know how to add and subtract binary, right? Or do you guys want me to go over that?
To add and subtract. I mean, can you do a subtract one?
Yeah. Can you build a problem? Oh, wait. I didn't write a problem though. Okay, let me find the problem. Hmm.
I don't think she's gonna have a subtract question on there. You can go to the side.
You sure? Okay, I'll come back to it. I'm just trying to find a good problem. Okay. Or I'll look in my notes and see if I can find one. Okay. So BCD addition. Where did I put that? Yeah, okay. So a BCD addition is kind of like a way it's kind of like a format question, okay? So if a group of 4 bits exceed the 9, then you have to add 6 to the group to make it into a number. So the best way to show this is through an example, okay? So I'm going to work this example with you guys. So you're going to get a problem like this. So you'll get X and then you'll get Y. You have to convert it to BCD and then you have to add it, okay? So converting to BCD is pretty easy. So I'll first do X and then I'll do Y. So it's just like how we're doing binary. We just convert each number to its own binary value, okay? So I'll do 5. 5 in binary is 0, 1, 0, 1. And then I'll do 4 in binary, which is 0, 1, 0, 0. 7 in binary, which is 0, 1, 1, 1. And then 2 in binary, which is 0, 0, 1, 0. Okay, so the BCD form of X is 0, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1. Okay, pretty self-explanatory to convert it to BCD. Same concept with Y. So our Y is 1, 8, 3, 6. All right, so 6 in binary is 0, 1, 1, 0. 3 in binary is 0, 0, 1, 1. 8 in binary is 1, 0, 0, 0. And then 1 in binary is 0, 0, 0, 1. So the BCD form for Y is 1, 0, 0, 1, 1, 0, 1, 1, 0. Okay? You guys understand how I got that? Okay. So now comes the actual adding BCD numbers, okay? So what I'm going to do is I'm going to color code each number based on the place that it's in, right? So 2 and 1, that's in the thousands place. I'll use yellow. 7 and 8, that's in the hundreds place. 4 and 3 is in the tens place, and then 5 and 6 is in the ones place, okay? So it's good to do that so that you don't get confused. So let's start off with the ones place, right? So we're going to add 5 plus 6. Yeah, so 5 plus 6. Our 5 value that we got is 0, 1, 0, 1, plus our 6 value is 0, 1, 1, 0. So you add that to as a binary number. So 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 in binary is 0, carry a 1. And then 1 plus 0 is 1. Wait, I did something wrong. 0, 1, 0, 1, 0, 1, 1, 0. 1 plus 0, oh, sorry, 1 plus 0 is 1. Plus 1 is 1. 1 plus 1 is 0, carry the 1. 0 is 1. Okay, right? So 1011 in decimal. What is 1011 in decimal? You guys know?
10, 11.
11. Good job. So 11. So 11 is greater than 9. So that's an invalid number. Okay, if our value is greater than 9, then it's invalid and we have to add 6 to it. Okay, so we're going to add 6 to this. So the binary for 6 is 0, 1, 1, 0. So we'll do the math. It's 0, 0, 0, 1, and then our carry will be 1. Okay, do you guys understand how I did that? Let me just. So now we're going to go to our next number, which is 4 and 3. So this is the tens place. So 4 plus 3, which is 0, 1, 0, 0 plus 0, 0, 1, 1. And then one thing to note is we have to use our carry from here and add it again to this. Okay? So the carry is 0, 0, 0, 1. Okay? Does that make sense? Okay. We're going to add our numbers, 0 plus 1 plus 1, 0 and then 0, 0, 1, okay? So 1, 0, 0 in binary is 8, which is less than 9, so we're good, okay? We don't have to do anything. Okay, let's move on to the next value. We have 8 and 7, so this is in our hundreds place, which is 0, 1, 1, 1 plus 1, 0, 0, 0. We have 1, 1, 1, 1. 1, 1, 1 in binary is 15. So that's invalid, right? Because it's greater than 9. So we're gonna have to add 6 to it. Okay? 1 plus 0 is 1, 1 plus 1 is 0. 1, 1, yes. Okay.
The number 9 is coming from the numbers, I mean, when it goes up to from 0 to.
Yeah. So that's just the general rule for BCD. If it exceeds that number 9, we have to add 6. That's just the general rule. Yep. So we'll do our last one, which is 2 plus 1. It's 0, 0, 1, 0 plus 0, 0, 0, 1. And then remember we have our carry. So we'll move our carry here. So plus 0, 0, 0, 1. Add that, you get 0, 1, 0, 0, which is 4 in binary, or 4 in decimal. So we're good, right? Because it's less than 9. Okay. So these are our final values. So your answer, you'll just put these together, right? So first we'll do what was in the thousands place. So that was this number, so 0, 1, 0, 0. Then in our hundreds place, we had 7 plus 8, right? Yeah, 7 plus 8. So 0, 1, 0, 1. And then in our hundreds, or tens place, we had 4 plus 3, which we got 1, 0, 0, 0. And then in our ones place, 5 plus 6, we got 1, 2, 3, 1. That is what your final answer should look like. Questions? No? We're good? Okay. Okay, fractional binary. So this is just to convert decimal to binary when you have decimals. It's the same concept as how we did it for just regular converting from decimal to binary. But when we have a decimal point, everything after the decimal point, it will be to the power of a negative exponent, right? So you'll be 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, 10 to the negative 4. Same with when it's base 2, 2 to the negative 1, 2 to the negative 2. And you guys get calculators, right? She's
No, you little use calculators.
she's not letting you guys use calculators?
Say you this lady something, this
Oh
lady
my
something.
gosh. Okay, so you guys are gonna have to memorize those values, like what 2 to the power of negative 1 is, 2 to the power of negative 2.
I mean, you don't have to memorize. If you're just quickly in the beginning of the exam, just put it on this side of the test.
Yeah. Okay. This is just a quick example. So you have 11.5625 and you're trying to convert that to binary. So the first way you do is you convert just the 11. So ignore everything after the decimal. So 11 in binary is 1011. And then so that's good. We don't worry about that anymore. And now we'll do everything after the decimal. So I like to do the multiplication method. So you take the decimal, you multiply it by 2. So when you multiply, you get 1.125. 1 is what's going to be in our answer, and then we'll take the 125 and we'll multiply it again by 2. Yep, and then we get 0. That will be in our answer. Take the 25, put it here, times 2, and then you guys get it. So once you get to the end of 1, that's when you know to stop, right? Because you can't there's nothing after, right? There's no exponent, or there's no decimal points after, so you know to stop. So yeah, then you put your answer together, 1101.1001. Okay. This is the opposite way, binary to decimal. So if you get this number and you have to convert it to decimal, you do 2 to the power. You do everything before the decimal first. Do 2 to the power 3, 2 to the power 2, 2 to the power 0, and then do the exponents, right? Same with this one. This is to hex. Do you guys have any questions about these? No? Good. Okay. Okay, fixed point binary. Okay, this is kind of tricky. I'll go over this one. So when you're given a problem, you're going to get it in this format. You'll get q n dot n, right? So the m means the total number of bits, and the n means the number of bits on the right side of the decimal point. Okay? So we'll look at a problem. I'll do this one. So 14.7, so it'll give you a question like this, and it'll tell you to convert it to fixed point binary, right? And then it'll also give you this, what the q is. So 8.3. This means that it wants 8 total number of bits, and then 3 of the bits have to be the right of the decimal. Okay. So first, we want to convert 14 to binary, which is just 1110, and then 0.75 to binary. So you do the multiplication method. 0.75 times 2, which is 1.50. You move the 0.50. So 0.50 times 2, which is just equal to 1. So that's when you know to stop, right? So your final answer for everything after the decimal will be 0.11. Okay, so putting them both together, that is 14.75 in binary. But to convert it to fixed point binary, so 8.3, again, it means that they want 8 total number of bits, and they want 3 to be on the right side of the decimal, right? So the way I would make this 3 to the right side of the decimal is I would add a padding of 0, okay? So now I'm at 1, 2, 3, 4, 5, 6, 7, and I'll add a 0 padding to the left to make it 8, okay? So that's how you get your binary, your fixed point binary form. Okay, yes?
What if the fraction, number of fractional bits you're allowed to have is less than a number? Because I once got a problem in homework like that, whereas like you could only have like two bits in the fraction, but the number I was supposed to convert had like 4 numbers.
Four
numbers in the fraction. Like, do you just like round? Do you just like chop it off?
Yeah, so in that case, you would chop it off, right? If you get extra numbers.
I don't think, because if you chop it off, then it won't be the same number.
But
think about it, right?
Yeah, it wouldn't be the same number. But I was because like, were you given like is there one on like one of the lab, when the lab arithmetic homework, there was a question like this where there's a number that more bits than can be put into the fraction. Do you remember that?
I can't remember.
You remember that? Okay. Never mind. Okay.
I mean, like,
Fine.
from just like thinking about it, right? If they give you that the n is less than the number you get,
Yeah.
the number of decimals or the binary number you get after the decimal point, it doesn't make sense, because if you chop it off, then when you convert it back, it won't be the same number.
Right.
So it's either like maybe they messed up the
Yeah.
or maybe when you were doing the math, maybe. Yeah.
Did we go over sign please?
Sign. Not yet. I think I'll do that at the end. Okay.
Okay.
Maybe. Yeah. Okay. Okay.
So when you add the zeros on, because I remember doing that, I had to add like 2 at the end, and I had 2 on the
Yeah. Yeah.
Sometimes it'd be like that.
Yeah. You just have to get it to that form that they want it, right? So they specifically wanted 8.3.
So the 8 stands for the bits, and the 3 stands for what?
The number of bits after the decimal.
Okay.
Okay. Yeah.
when you're doing that question, do the 3 first.
Like the
You know where'd the question go?
This one?
Yeah. So you know the 3 is the bits to the right of the decimal point. Do that first, and then you find the total number, and then if you need more, add it to the left side. Yeah.
Okay, so this is the last thing I'm gonna cover. Floating point binary, or also IEEE single position floating point format. Okay. So the way they want this is 32 bits total. Okay, your answer should have 32 bits in total. So 1 bit will be your sign bit, so 0 or 1. 8 of the bits will be your biased exponent, and then 23 of those bits will be your fraction or your mantissa. Okay. I'm gonna show you guys an example because that's the best way to understand this. So we're gonna do 11.25 converted into IEEE format. Okay. So what I'm going to do is the first step is always convert 11 and then 0.25 into binary. So I'm going to first convert 11 into binary, which is 1011, okay? And then I'm going to do 0.25 into binary, which is 0.01. Okay, you would do that multiplication method, okay? So that's the first step. Your second step is to put this into scientific notation. Right, so right now your answer looks like this. To put into scientific notation, it's the same concept we just do in math. You move the decimal like an amount of time so that the decimal comes here, right? And there's only 1 digit in front of the decimal. So by moving the decimal, we get 1.01101 times 2, and we moved it a total of 3 times, right? So times 2 to the power of 3. Does that make sense? Yeah. Okay. So this 3 is your exponent value. So that's what we're going to use for that 8-bit bias exponent number. So what you do is you add 3 plus 127 to get 130. Okay? So that's your exponent number. So that's what goes in the middle. So then you do 130 into binary, which is 1, 1, 2, 3, 4, 5, 6, 7. Okay? So that's going to be that middle number, that 8-bit middle number that goes right here. Okay? And then the last thing is the mantissa. The mantissa is pretty easy. It's just this number, just whatever comes after the decimal, and then you pad it to 23 bits. So your final answer would look like, so first you have a sign bit. So in this case, our sign bit would be 0 because we're we have a positive number. So 0 would be our sign bit. Then we have that 8-bit exponent number, which we calculated to be this. So 1, 1, 2, 3, 4, 5, 1, 0. And then we have that 23 mantissa, which is this, once again, it's the number after the decimal point padded to 23. So 0, 1, 1, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then you keep going until you get 23. Okay? So that would be your final answer. Does that make sense?
That 130, can you do that converting from 130 for me?
Yeah. So you get how we got that, right? We just converted 11.25 into binary. And then
I just need
the exponent.
130.
Oh, that's just converting 130 into binary. You know when we do like 130 divided by 2?
Oh, okay.
Yeah, it's just that. Sorry, I didn't explain.
I'm trying to do it with the 4 digits.
Oh, no, sorry, I didn't explain that.
Okay.
But you got how we did this, right? You just add 127 to the exponent. Okay.
I remember that.
Okay. Okay, this is IEEE to binary. It's basically we just do the opposite of what we just did. So the first bit we know is our sign bit. It's 1, so that means it's negative. We'll take 8 of those bits for the exponent. So if you convert this into an exponent, you get 131, right? Then you just subtract 127 from it, you get 4, which is 2 to the power of 4. And then the rest is your mantissa. So you would only take 0, 1, which is 0.01. So this is what your final answer would look like. You have a negative from the sign bit, you have 2 to the power 4 from here, and then you have your 0.01 from here. Okay. Okay, shifter. Okay. Do you guys have any questions about any stuff on here? Okay, ma'am.
Okay, actually, honestly, I do. Like for it's converting so product. Let's see, one on one. Product of sums is like when you have all the things multiplied by each other, right?
Yeah.
And so do you think on the first exam there's a problem where I had to convert that to sum of products?
Mhm.
Do you think that that'll be on this exam again?
Did we have that?
Like,
There could be,
There could
because
be.
it is cumulative, right?
yeah, it is cumulative. It's like that. I had trouble. I know you have to use some rule, and I had trouble. I had a lot of trouble with that.
I looked at the example that Deeks just sent, and I couldn't see any on there.
From what I remember, I don't think there's like one big question with
Yeah.
all of the concept of KMAP.
Like there might.
We had it.
Yeah.
Okay.
I don't know if they changed it, but I remember there was like one of the later questions.
Yeah.
It was like one big question, then they gave us the equation. They were like, turn it into a SOP, POS.
Yeah, I know how to do that.
That one.
I know how to do that.
Yeah,
Yeah.
I don't think there's any conversion between SOP to POS.
That's good. Okay.
They might give you like an equation where you have to like simplify it.
Yeah.
Yeah. Okay.
Do you guys want to do practice on that, or are we good? You want to?
Well, you mean like the Boolean expression?
Yeah.
Yeah. We can
Um,
do a KMAT too.
Yeah, we can do it. I have to find a couple for my notes. Let me see. Okay, so yeah, no, it can get confusing. Right now? Actually, she has to leave, so she's gonna quickly go over her comparator stuff, and then we'll come back. Is this long?
No, it's fine. It's just the first. I'm gonna be going over these. The questions that are on this one were not the one that I had put as example. So I'm just gonna change these. Okay. So if y'all remember load word, this is where we take read in data from we read it in from the data memory and we write it to our register file, right? So same thing over here. This one is our RS. This is our RT. And this is our IMM. So all of these, the binary number, we can find it over here, the opcode and the address. Okay, and this table is given in the exam, so you don't have to remember these. So load is 23, so it should be here. Let me. '23 should be 100011. And if you remember, this is a I type, so it's this one. So we have the opcode RS, RT, and then the IMM. So this is the opcode, and then we get the RS, which is 0. And if you look at the table, 0, it's just 0. Or sorry, it's actually 8 because it's T0, right? And so the binary is 0. I'm so sorry. This is actually RS and RT. I messed that up. The opposite, because this is where we're reading it in and this is where we're writing it, right? So RS is 5, which is 13. So that would be 01100 or 01101. And then our RT is 0, which is 8. So it should be just 01000. And these are all the numbers in binary. Right? I just get the number from the register, the address, and I write the address in binary. That's how we get it. And our IMM is just 0, right? So that's just 16 bits of just zeros. Okay? It's just 0, 0, 0 until we get like 16. Okay? And so to writing it actually in the equation, you see how they give the numbers? So if we just look at our number and we just take whatever the numbers are in that placeholder. So we're gonna be writing, right? Since we're writing it to T0, so the enable is 1. Okay? And we will also be reading it. So all of the read ones should be 1 as well. And this is the data memory. We're reading it from the data memory, right? Do you remember this is the data memory? We take whatever the content is at T5 and we add 0. So we're reading it from the data memory. We're not writing to the data memory. So that's 0. And so if we just go down here, right? So this one, the add, it should be take whatever we start with 0 and then we go to 32, right? We just take whatever the numbers are associated with it and we just write it down wherever it's like the 21 to 22. So mainly focus on getting your binary correct. And if you get that, this is just filling it in the question. Okay? And then the other main things is just getting the read enable, write enable, right? So for load words, as I said, we are reading it and we're writing it to the RF. We're not writing it to the DM, so we just leave that as 0. The operation we're doing is add because we're doing the content as at T5 plus 0. So we're adding it. That's why it's add. And again, the control we are writing to the RF. So that's 1. So the first, when we're writing it to T0, right? So, and that is 8, so that's the binary for that. The data we'll be writing should be, so let's see, T5 is 44 plus 0, so it's just 44. Right? And this is actually wrong. It should be 44. So the data memory at 44, we have 289, right? So we just write that here, 289. And we don't have any other data read, so we just put NA. We're just reading one data right here, which is a T5. And yeah, so it's 1 here, right? All right, write enable is 1. So we get the number from T5, which is 44 right here. And if you look at, it's just zeros, right, at the end, since the IMM is 0. So the 16-bit is just 16 zeros here. So this is again just zeros. And our operation is add. So it's 0, so we're adding nothing. So we're adding 44 to 0. That's why it's 0. And when you do 44 plus 0, it's just 44. So that's the data address, which is here. We got this one, right? Yes.
Yep.
Okay.
Shippers, yeah,
I guess it has to be machine code. That's a good idea. Let's look at that.
So for the machine code, so ADDIE is a, if you look back, it's a I type, right? So I type is this one. So the opcode would be the opcode of ADDIE, which is 8. So it should be 1000, and since it's a 6-bit, we add zeros at the end. This is our RS, or sorry, that's RT, RS, and this is the IMM. And it's kind of confusing, but like it kind of switches to the RS. Actually, we write the code for RS first, and then we write the code for RT, right? So this is the opcode. R
the 8001.
here from the table. So ADDIE, it's in hexadecimal, right? But it's 8, so opcode is 8 in binary, and you just add zeros to make it into 6-bit. It's like the padding that she was talking about. And RS, if you go back, so it's T3. Again, it should be in the table. It should be given 11. Again, you just write that as binary, so it should be,
Question.
yes.
And you know for sure that table's gonna be given to us?
We were given.
We were
Yeah,
given.
she says we give it
Yes.
yesterday. She says
You got a 4.
Yeah.
Oh, y'all don't have RT. And she's different.
But
She might expect.
she did.
Unless-
She did say we're gonna get this. She did.
Oh,
Say
yeah,
Okay.
she did say
She did
that.
say we're
yeah,
gonna get this.
so you're gonna get these 3 tables. Okay, but I don't know, you weren't there in the beginning, but this is another thing that we added. You should memorize this. This is just the way the format of the code is.
Okay.
Yeah, this is not given. All of the tables are.
Okay.
So going back, RS T2. So you don't have to memorize the numbers for T2 or anything. Just memorize where RS, RT, and RD are for all of the different codes, right? So for add, there's 3. So there is. I'll do another example after this, but okay. So RT is T2, which is 10. So it's 0, 1, 0, 0, 1, 0. And IMM is just 25 as binary. So it should be 16, 8,
Lecture.
1, 2.
This-
Yeah. Just trying to do it in my head. 1. Yeah, 16, not 8, and 1. So that's 25. Binary. Does that make sense? It's just 16, 8, 4, 2, 1. Right? And the IMM is 16-bit. So you would just add padding in the beginning till you get 16 bits. That's it. So to write the whole binary, so you have the opcode, which is 0, 0, 1, 0, 0, 0. RS. RS is 0, 1, 0, 0, 1, 1. RT. 0, 1, 0, 0, 1, 0. And the IMM, so you'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. 11, 12, 13, 14, 15, 16. Yeah. Just make sure you get the number of zeros in the beginning right. But yeah, that's how you do ADDIE. And okay, for this one,
What is it? Branch and the bones? What are those used for?
the which one?
What are they, like branch or B and E and
Branch not equal to.
yeah, B.
Yeah.
What are those used for?
What are those used for? It's like an if statement. You compare the different branches.
So you're talking about like in MIPS.
Yeah, right.
So So it's like, you know how if statement works, right?
Yes, sir.
If statement.
Oh, okay, right.
So like if you were hypothetically doing an if statement, if this digit is not equal to this number, jump to this line, right?
Right.
That would kind of do something similar. So on so we would write B and E, and then our values, and then on the last one we'll write which line to jump to, and then it'll go all the way down there. If that makes sense.
And that's what the same thing for like the BQ. Like I'm just trying to figure out the add, and all that. What's the difference? Like, how do you-
So adding and add is like you have the numbers from the register file, and you do the addition and subtraction. But the BEQ and B and E, you get the register files, where the registers are, and you compare what the data is in it. If that makes sense.
And then
Yeah.
and then label one, it will just jump to label one. Label one is kind of like its own function.
Yeah, it's like if you think of it in a code, right? So you're like, if 5 is greater than 2, then do this, kind of like that. But in this one, it's like kind of if it's equal. So if the data in these two are equal, jump to this line in the code. Yeah.
If not, then it'll just skip it.
Yeah, it just continues down whatever your next line of code is. Okay. I'll go over this one since we were just talking about this one. So BEQ is if branch equal to, and this is also a I type. So we have the RS, RT, and IMM. So again, you get the opcode, just 4, so it should just be 0001000. This is the opcode. RT, so this one should be RS, RT, and you have to memorize this to know which one is RS and RT.
Are they in the same order for like the other types?
Here. So RS, RT. They're in the same order for the equal to and not equal to. But they're different for ADDI and add.
Because they're completely different types, right?
Yes, because it's completely. But if it's like the comparison, they're the same. Yeah. Yeah, and then this one should be just the IMM. And this is a formula that I was talking about in the beginning, this one. So with the address of the label, so all of this should be given. So the address of label is 40, right? Minus the address of the branch plus 4. So we are given the address of the branch plus 4.
We're given it in hexadecimal, right?
Yes.
So,
Yeah, we're supposed to convert it. Yeah.
so we can still do the plus 4 to. Okay.
Yeah.
You convert it to decimal.
We have to convert it to decimal, but y'all know how to do it from hexa to the. Shoot, we went over this one, right, before? Or no?
Converting.
Hexadecimal to binary.
I showed the chart. I didn't go over it though.
Okay. She'll go over it quickly, how to do that.
Yeah.
But it's pretty easy. You should have learned how to do hexa to decimal.
Hexadecimal.
Yes. That's what you do over here. Yeah. Like, I won't go over it just for time, but. Yeah, and the number should be. Do the math correctly. It should come to 36 in binary, or decimal. That should be the answer. And this is the IMM. Should I go over it again? I know it got confusing, so how to find the IMM for this one is you take the address of the label minus the address of the branch plus 4. And in the question, it would be given in hexadecimal, and you have to convert it into either binary or decimal, and you do the math. Okay? And for this question, it should be 36 in decimal. Yeah. So this is our IMM, and we would convert this into
As long as it's nice.
into binary, and
The copy paste that do the
should be
I wanted to teach forever and ever.
Oh my god, our goat is here.
yeah. And so again, same thing as before. This one, these two should be given. 5 is 13, so that's 0, 1, 1, 0, 1. T0 is 8, so it's 0, 1, 0, 0, 0. And the IMM, you convert, again, you just convert this into decimal, and you do the padding of the zeros until it becomes 16-bit.
Did you say that we chop the 2 zeros at the end of?
Yeah. It would be 0.
Yeah, 2 zeros in there.
Yes. Yes. Yeah. Yeah. Here, let me just do that. What would be 36 and 16, 32
36 hexadecimal?
in binary?
Is 36 a decimal or?
36 is a decimal. 16 is
It's to the fifth.
here. Huh?
It's to the fifth, and then one.
That's smart way to think about it, yeah. So it's 1, 0.
Yeah.
Like 1 0 0 1 0.
Yeah. So you see these four zeros, right? The last two. 36 in decimal. 36 is a decimal in binary. If you convert it 1 0 0 1 0 0, you take these two zeros and you put it in the front, and just kind of cancels out. It's 0 because if you're moving in the front and you add more padding, right? So it should be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So these are all the padding numbers, and this is our actual IMM. And to understand why we're taking out these two numbers, we already know it's a factor of 4 because we're having the 4, right? That's why. So it's like we know it's going to be a factor of 4. That's why we take to 2 zeros at the end. We move it just to get to have to not waste the bits, if that makes sense. Because it's just zeros, right? And we know if it's a factor of 4, in binary it's just going to be 1 0 0 always. That's why. Just take the last two zeros off just to save the bit, and we just add more precision in the beginning. So the answer would be 0 0 0 1 0 0. RS, which is 0 1 1 0 1, RT 0 1 0 0 0, and then the IMM. This whole thing is IMM, and it would come here. Any questions?
Like this is not about this one, but for store. So for load word, the RS, and it's like RS. Like it's RT and then it's RS, right?
Yes. So for load, it is R.
Yeah.
Let me.
Is it? Like, my question is it flipped or store word? Like, is it flipped or is it the same way that the first number is the RT, the second is the RS?
This one's really good.
Because they say you have a store word, T
Mhm.
something, then the 0 T something else. Because the RT is like I don't know. Is it flipped or the same?
Are you talking about? Okay, so
store.
it's the same thing here. So this is RT.
Yeah, that's RT.
This is also RT.
Okay, good to know. That's
RS.
thinking about destination, but it doesn't matter because there's no RD. Oh,
Yeah,
RD.
the load work and the store work has no D. There's only S and T.
So it's I guess I was thinking of tell me here's the destination and the origin are flipped between load word and store word. That doesn't matter. Well, because where we're taking the data and we're removing it, it doesn't matter. I learned what I thought. You do not flip it. It's RT. Thank you.
Yeah. Okay. And Yeah. Anything else you want me to go over? Do you want me? This is the same example.
I guess like, no.
You want me to go over this one? It's the same thing. You get the opcode, you get the address over here, this one, and this is the IMM.
So like, so RT always before R? Well, no, it's not. Sorry, ADDI RS is before RT, right? Well, 'cause,
Or-
like when we're taking, because like we take the numbers because like in the machine code, RT
Mhm.
is always before RS, but the ADDI, you know,
Yes.
how it's like the value we make the RS is before the RT value, right? Because like you know, because
Okay, ADDI. Okay, here. ADDI, right? It's RT, RS, and then the IMM, right? For load worth is also RT, IMM, RS. Store worth RT, IMM, RS.
it's alternate. Like RT is always before RS.
Yes, in the load worth and the store worth.
Yes.
Yes, the LW and SW, RT is always before. And ADDI also the same thing. It's just the IMM is like switch with RS. And for addition and subtraction, it is RD, RS, RT. Destination, first argument, second argument.
So like I can't like read it at this distance, but in the opcode for the R type, you scroll down there because the RS comes. I see. Okay, so then in the opcode, I was wrong before. So the RS comes before RT
Mm-hmm.
in the opcode. So
Yes, always.
That's good to know. That's very good to know. So
Yes.
you always have to flip that.
So in this one, when you're taking it from this
Yeah.
to the decimal,
Yeah.
right? When you're writing it into the machine code, we would switch the RS and RT.
That's very good to know. So
Yes.
flip it, like RT. That's very good to know.
And then when it's the addition, subtraction, the R type, you just move the D at the end.
Yes, I do recall that.
Yes.
But, yeah.
And the S and the T are in the same line.
Okay.
The D is here.
So,
And then we have the
so
shift.
You answer my question.
And it's the same thing for subtract and multiply. Yeah. I think that's it. I was gonna go over this, but I guess it won't really make sense for y'all because if you haven't even looked at it, I don't think she's gonna go over the review. So
I guess that's something you could probably derive, but I guess it's gonna.
I mean, I'm just gonna go over it quickly. It's the same thing. You know how we did the machine code, right? Whatever the machine code is, it's 32 bits, right? So we're gonna have whatever the really long number. This side, the leftmost is 31, rightmost is 0, and you literally just copy paste whatever the number are in that placeholder. So from 31 to 26, whatever, if it's 0, 1, whatever it is, you just write it right here. That is it. Same thing over here. Wherever it says like IR 20 to 16, just take whatever the numbers are in that position and write it. And then for the enable and everything, just if you understand what a SW and LW does, you can just write that. You know how like load worth, we read from the data you read from the data memory and you write it to the register file, right? So just think about it. Are we reading from the DM if it's a load word? Yes. So that'd be 1. Are we writing? No. We're writing in the register. Yeah, this would be yes. Right? So it's kind of like if you understand what you're reading, this should be pretty easy. Yeah. And yeah. And I think you're going to go over the last couple of stuff, right?
Yeah.
Okay.
It's just let's go over the stuff that we like missed. You guys want me to go over decimal to hexadecimal conversion, or hexadecimal to binary?
Can you mainly do IEEE representation?
Oh, it's very.
I'll
That's very common.
I'll go over with you after.
Like personally, I like to see adding shifting. What do you want to see? Like what do you do?
Adding and shifting, okay.
Hexadecimal ain't that hard.
Can you get my phone? I have an example on there.
So I remember like you take the 4 bits and like wherever it's in binary, you take 4 bits, you convert that to a hexadecimal number, and you do the
And if it's over, I think if it's over.
Pretty creepy here. Wait, just you can stop it.
Oh, yeah, that's what BCD does.
I'm just gonna like random stuff. Okay.
That's decent.
That's different.
Wait. Can I stop screen? Or never mind. I need to screen share, cause that's how they
I will
see.
stop recording it.
And I'll join on my own computer.
No, you don't have to.
Wait, don't you need your computer? Can you come back and get it?
1 second. Let me stop this.